it. Digital image correlation. Digital image correlation is a method of taking distances that would not be taken otherwise. By measurement, the movement of particles attached to the sample while it's being axially loaded, true strain can be discovered. The difference between true strain and engineering strain is that engineering strain is more of a net measurement of true strain's actual value. True strain is a precision measurement done through expert tools. Engineers use engineering strain because they only need a net measurement. Next slide. Okay.
So the process of setting up this test is very similar to a conventional tensile test. The first thing we do is to measure the length, width, and thickness of the samples, and then to place them into the tensile tester. One of the differences between this test and the regular test is that this test requires speckled samples. In this case, they were speckled with black spray paint on white paint. It then uses a camera and fancy software to record the deformations of the samples and during the test being performed. There's a couple of things to consider when setting this test up. The camera must be aligned perpendicular to the sample and properly focused, and the sample has to be well lit. To be correlated with the displacement load data.
This is our Plastic One data. Here we have our lateral strain in yellow, axial strain in red, and displacement in purple. It shows the material going through a elastic change as it is being pulled, and with that data we can calculate the Poisson's ratio. We compare that Poisson's ratio with the high and low known densities of plastic to get a wide breadth, and it is more closer to high density plastic. Here we have our first stress versus strain graph showing a plastic broken up through grip tightening and a stress versus strain graph. Here we have a corrected plastic variation with a strain on the x-axis, strain on the y-axis, and the displacement, all purposely showing a Poisson's ratio, comparing it to the difference between the literal values and the high and low densities inclusion with the difference. Here we have plastic 2 stress over strain graph that was taken from the videos recorded from the lab. Here we have copper 1. Copper 1 shows an unusual interference action when being recorded on the x-axis for strain as it gains a little bump. This can be explained by a lack of speed in the beginning and then a further acceleration once a notice for more speed was inputted, thus creating a imperfect value graph, but with a 0.17% difference between the limited value and the Poisson's ratio. Here we have the stress over strain graph for that first copper, and then we have copper 2 showing a more correct Poisson's ratio relationship between lateral stress and axial stress with a displacement graph included. Here we have copper 2.
So here we can see our very best aluminum sample. We see that our calculated Poisson's ratio is less than 0.1, and this is against the literature Poisson's ratio of 0.33. This gives us a difference of about 70%, which is crazy. We can see that the displacement is fairly linear during the test, and yet the strain in the X and Y is very jagged. There is some mirroring of the displacement if you were to plot a trend line, which we haven't, but I think these jagged edges are due to the dislocations of the material. And yet our elastic modulus, our hand calculations, came out looking pretty good. I mean, there's a very distinct linear region. You can see a little bit of toe down at the bottom, and then it yields and moves on to the plastic region. Here we can see our second aluminum test, and this one was giving us some really wacky results. You can see that the Poisson's ratio is over 1. Ignore the fact that it's negative. It's over 1. And you can see that despite the displacement being fairly linear, the strain in the X and Y direction was extremely jagged and did not follow the curve at all. Again, we have a very nice stress strain curve with a little bit of toe, a yield linear region, a yield and plastic region. So as you can probably tell, we ran into some pretty serious issues during this test. The first issue, which was fairly minor, was an alignment issue between the camera and the sample. Then we ran into timing issues as we were not able to trigger the load displacement camera at the same time as we triggered the digital image correlation. We ran into some fairly serious material issues. We went through like 6 aluminum samples before we got the samples we showed you, and those were really the best ones. And finally, we ran into issues between the software, just using the software, and analyzing the data. The first was the reference scale factor. There's no real good way of getting a very accurate reference scale factor. And second was the coordinate setup. The system would not set the same coordinates twice in a different project, and it was very irritating. Finally, another issue we ran into was units. The tensile tester, the load displacement tensile tester, measured in imperial units, and the software measured in metric units.
In conclusion, the Poisson's ratio is important because it allows us to calculate the material's behavior in different loading scenarios, thereby determining the shear modulus and the bulk modulus from a simple and straightforward tensile test. Poisson's ratio allows us to do that, and